I still remember in physics class seeing the double-slit experiment and just thinking, wow, it seems so clear that light had to be a wave to cancel itself out like that.
And for a century, that idea wave-particle duality has been, the bedrock of quantum mechanics.
Right.
But now, just imagine physicists coming forward and saying, we might not need the wave model at all.
To explain that classic experiment, how...
That's what we're digging into. A radical new idea called dark states at the quantum level and how it connects to the cosmic level mystery of the theoretical dark photon.
Okay, let's start with that first claim because it's a huge one. If photons are only particles, how on earth do you get those dark fringes in the pattern, the spots with no light?
The new thinking is that it's all about quantum states. Think of them as bright and dark.
Bright and dark state.
Exactly. The bright fringes we see, that's where photons are in a bright state and they can interact with the atoms on the screen. But the dark fringes aren't empty. The photons are there.
They're there, but we don't see them.
Because they're in a dark quantum state, they're invisible to the detector. They just can't interact with it in that moment.
So, wait. If the photon is physically at the dark fringe, why wouldn't we have detected it? I mean, for 100 years.
It's not a flaw in the experiment. It's actually a deep consequence of quantum mechanics itself, of superposition and entanglement.
Okay.
The single photon goes through both slits at the same time. And whether it lands bright or dark depends entirely on the difference in the path length from each of those two slits.
So if the paths are in sync, it's bright.
It's bright. And if they're perfectly out of sync, the photon is essentially forced into that dark, undetectable mode.
That is profound. Dark just means invisible light. So let's scale this up from the quantum to the cosmic. If light can hide like that, it sort of lends weight to the idea of a whole hidden dark sector, right?
It really does. It makes the idea of dark matter, the 84% of matter we can't see, feel a little more plausible.
And this is where the dark photon comes in.
Yes. The dark photon is the theoretical force carrier. It's the proposed portal between our visible world and that massive invisible dark sector.
A portal. And the hunt for this portal, I understand, has gotten really serious.
It has. Recent analyses of particle collisions, deep inelastic scattering, are now strongly favoring the dark photon hypothesis over our current standard model.
And the confidence level is high.
Incredibly high, 6.5 sigma. In particle physics, 5 sigma is the gold standard for a discovery. So 6.5 is, well, it's evidence. It tells us something new is almost certainly going on in there.
A 6.5 sigma result. I mean, that kind of precision doesn't just happen. You must be sorting through just petabytes of data to find that signal.
Oh, absolutely. The computational challenge is immense. Organizing it, training models to find the pattern, it's a monumental task.
And that actually brings me to our sponsor. This deep dive is supported by Embersilk. If you're working with vast data sets or need help with AI training, automation, or software integration to speed up your own discoveries, you should check out embersilk.com.
It is a relief for the research teams that the search is, relatively focused. For the massive dark photon, they're chasing just two numbers.
Two numbers. What are they?
Basically, its mass, how heavy it is, and its mixing strength, which is just how weakly it interacts with normal matter.
So you narrow down the possibilities.
That's the goal. Experiments at the LHC, JLab, Phaser, they are all aggressively closing the windows on where this particle could be hiding. We're talking a mass around 200 times an electron and an interaction strength that is just incredibly faint.
And the prize here isn't just one new particle. It's potentially confirming an entire new sector of physics that governs most of the universe. It's a confirmation that reality is so much richer than we see.
Which, brings us full circle. If light interference is just photons slipping into a dark, invisible quantum state.
Then could that apply to matter, too? We know electrons, even whole molecules, create interference patterns.
Exactly. Does that mean they can also shift into these undetectable dark states?
So matter itself could become temporarily invisible to us through entanglement.
That's the provocative question, isn't it? It suggests that the universe has this whole other gear we're just now learning to see. There's just an incredible time for discovery.
Absolutely fascinating. If you enjoyed this exploration of how hidden physics is redefining reality, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.